All right, section 3.1 is called Linear Approximation. And this is actually quite similar to stuff you've already done. It's just got a different name for it. So even the notation, as I show you the notation, I'm going to show you, hey, you've already done this. It looked like this before. All right? So let's start with first what this is actually talking about. Linear approximation is the idea of finding the exact value of a function that's difficult to calculate. For example, let's say we had f of x equals the square root of x, and x is equal to 4.1. Well, I don't know what the square root of 4.1 is, not exactly, and neither do you. But you know the value that's very close to the square root of 4.1 because you know the square root of 4, right? So this is an idea of approximating using what you do know about the information. So notice a nearby value we know is when x is equal to 4. So we could say that f of 4.1, like the square root of 4.1, is about the square root of 4, which is about the answer 2. It's an approximation. But we can do better than simply ignoring the little difference that we're off by. We can also approximate the difference we're off by. And the way that we can do that is by finding a tangent line. Well, finding tangent lines is derivatives, right? That's everything we did in chapter 2 is about finding these tangent lines, finding these derivatives. And we can figure out on the tangent line what the value would be at 4.1 instead of being on the graph itself. This value on the tangent line will be approximately equal to the value on the curve. Now, you'll notice on the notes that you have, there's some space over here, right? Looks a little bit awkward as it's currently drawn. The reason I want to draw that for you is because why I have that space is because I want to draw you a picture. I don't know if I have a slide in here to do that on. Well, this one will work. Let's write this down and then I'll draw you the picture since I've got it up here because you're not going to listen to me if I don't just let you write it down. The linear or tangent line approximation of f of x at x equals x0 is the function. L of x equals f of x0 plus f prime of x0 times x minus x0. But here's the kicker. L of x is simply y. F of x0 is what you usually call y sub 1. F prime of x0 is what you usually call m, right, like slope. And this is x minus, and again, x0 is what we usually call x1, or maybe you call these x0. What is this an equation of? It's just a line, right? So if you don't like the way that this is written with the notation looking different, you can start out. You're just finding y minus y1 equals m times x minus x1. That's all we're doing. We're just finding tangent lines. Really all we're doing is tangent lines in this section, okay? So here's the idea of the picture. So I'm going to draw you the graph of the example that I just mentioned above, which was the square root of x. So the square root of x looks roughly like this. And we're going to say the x value is 4 here. And basically what we're saying is that we could draw a tangent line right here through this point. And that's fairly believable, I think. And the idea being that if I were at 4.1, which we'll say is right here just for the sake of being able to draw something, that the value of 4.1 on the tangent line and on the graph of our equation itself are almost the same, right? They're very, very close together because that's the whole point of a tangent line. It's supposed to touch the graph only at the point we want, but be very nearby to the rest of the curve, nearby the curve, right? Nearby that particular x value. So the difference in these two x or y values at this particular x value is very, very minor. Very minuscule. So basically what we're going to do is we're going to try to figure out, okay, I've got this equation. What is my tangent line at the point I'm looking at? And then I'm going to evaluate the point I care about at that tangent line instead of at the equation I was dealing with to begin with. Okay, that's the premise of what we're doing. So we're going to do this exact question that we've been sort of dancing around in the last definition. We're going to find the square root, an approximation for it, the square root of 4.1. Okay? Now, they tell you x0 is equal to 4. You should know that. I shouldn't really have to tell you that. You should be able to look at square root of 4 plus 4.1 and say, you know, that's almost 4. Agreed? Okay, just checking. All right. Yes? Okay, I thought I heard something. All right, so the idea here is we're going to find the tangent line. So I need to find the derivative. So let's find f prime of x. So what is the derivative of square root x? Good. 1/2 x to the negative 1/2. Everybody good with that? And of course, we can rewrite this, especially because we're about to evaluate in a moment, as 1/2, and then the x to the 1/2 will be in the denominator because of the negative, and then 1/2 is square root. The next thing we're going to do is we're going to evaluate this at the x value that we can do it at easily. I mean, that's the whole point, is that I can plug the 4 in to the square root x, which is still part of my problem, and I can get a calculation that I know easily, quickly, something I can do with just basic, knowledge of math that you've done thus far. All right, so I've got 1/2 square root 4, which would give me what? 1/4. And this is my slope, right? And that's what derivatives give us. They give us slope. So in terms of the equation, I'll use the notation you all are familiar with. This is y minus y1 equals m times x minus x1. So we have found m. I need to find, and we're given x1. What's x1? Do you know? This one is the 4 value, okay? This one is 1/4. What is x? Well, you know what, let me just pause there. Let's find y1 first. How are we going to find y1? What's that? It gives it to me. It doesn't give me y1. It gave me x1. Isn't what a point?
Isn't the square root of 4.1?
It is a point, but the 4.1 is an x value, not a y value. I'm looking for the y value.
It's the square root of 4.
Right. So this value right here is supposed to be the y value when I plug in this x value. Okay? So if you take a look back over here at the formula, this is the f of x value that I can evaluate without using the calculator. I mean, that's pretty much what it means. We're about to see one that's not going to be a great example, but because we have to actually use a calculator. But anyway, so this y1 value is supposed to be what I find when I actually do the square root of 4 in this case, which would give me 2. All right, so my tangent line, or my linear approximation, is actually y minus 2 equals 1/4 times x minus 4. Now, we can move the 2 over to the other side. We can call this, and if you look in your book, they are not going to have it written that way. They're going to write, instead of y, they're going to write L of x. They're not going to have the 2 written on the left. They'll have the 2 written on the right, like this. And then they'll have the x minus 4 here. This is what it'll look like. But you should be okay with the fact that that's exactly what we already found. In either of those forms, it's the same thing, right? Okay. What we want to calculate is we want to calculate what happens at 4.1. So I don't really want to simplify and distribute the 1/4 through that. I really don't. And the reason I don't is because I want to plug in 4.1, because what is sort of friendly that's going to happen when I plug in 4.1? It's going to be almost 0 there, right? It's not exactly, but I'm going to have 4.1 minus the 4, so I'm going to get a 0.1 right here. So I end up with 2 plus 1/4 times 0.1. And then if you want to use a calculator to multiply decimals, fractions, that's fine. It's not a big deal. But we're going to actually multiply 1/4 times 0.1, and then we're going to add the number 2 to it. And what do we get? It's 2 point something. 0.0, that's right. What'd you get, Edgar? Yeah, it is 0.025. Now, just for fun, this is the answer to the question, but just for fun, how could we check to make sure that we have at least a reasonable answer? There's a couple of things we can do. That's the very first thing. It better be close to the first y value we found, which was 2. Is it? Yeah. The other thing you can do is you could actually take your calculator and find out what is the square root of 4.1, right? And make sure that the value is close to what you're working with as well. So just for fun, real quick, what is the square root of 4.1? Approximation in your calculator, that is. 2.02485. and I got 2.025. That's very, very close, right? And to have gotten the answer that the calculator did, it actually used numerical methods of iteration to try and get that. It didn't calculate anything that you can't do. It just did it with a lot of steps involved in something else. So this is a very close approximation. All right, we're going to do another one. The next one we're going to do, I think, if I remember right, has trig in it. Yep. I will tell you right now that this is not my favorite example of doing this. It works just fine, but kind of the point of doing linear approximation is that it avoids you needing to use your calculator to calculate something. And we're going to see at the very end we actually have to use our calculator anyways on this one, which kind of defeats the point. So I'm not real fond of that. But nonetheless, there's an example or two in your homework that use this, so I wanted to show you how you would go about it. Okay? All right, so the first thing I want you to recognize is that sine of 1 is not a unit circle value. It's not 1 pi, this is 1. Okay? But there is a value in terms of pi's that is close to the value of 1. Any idea what it might be in terms of pi that's awfully close to 1? Let's think about it this way. Several of you guys were at Pi Day yesterday, celebrations, right? Right? That's okay. If you forgot, it's okay. Several of you were there. Pi is approximately what? Yeah, 3.14. 1.1598. A lot. This is the Pi Day of the century, and if you don't know what that means, just Google it and you'll see why. But this pi value is kind of roughly 3, right? So what would I have to divide it by to get roughly 1? Think unit circle, though. I don't want to... Oh, I think you're giving me the answer is what you are, aren't you? You're not telling me what to divide by. Yeah. You would divide by 3, right? I should put an approximation. This is not exact, obviously. It's an approximation. So 1 is about equal to pi thirds. Agreed? Why do I like that? Well, I like that because I know from unit circle what sine of pi over 3 is, or at least I should know from having trig recently, just like you all have, right? So let's think, what is the sine of pi over 3? It's, somebody said 6. That can't be right. It's got to be between -1 and 1. It's going to be a little bit off. Point what? 866. Maybe that's what I heard. I'm sorry. So what would that be in terms of like radicals? Do you remember? Somebody's got it. Square root 3 over 2. Yeah, so this is square root 3 over 2. If you do not know unit circle stuff still, if that's not sort of fresh on your mind, go back and look at it to help yourself out. This is square root 3 over 2. Okay? So the cool thing that I have found out right now is that this right here is x0, and this is y0, or x1 and y1. I don't care what you label them. It depends on what you're using. So in terms of my equation, I'll write it with zeros now since I just wrote that down. I'm going to do y minus y0 equals m times x minus x0, and I know x0 and y0 now. What do I need? I need m. So how do I find m? The derivative. I need the derivative of the sine function. So if you think about this, what we're saying is that my function f of x is sine of x. So I need f prime of x. So what is the derivative of sine x? Cosine x. Okay? But I don't really want the derivative in general. I want the derivative at a specific point. What point? Pi over 3, because that's the evaluation point that I used before for my x value. So I'm going to find specifically f prime at pi over 3, which means I need the cosine of pi over 3. Your calculator's a little bit friendlier on this one because the answer is actually 1/2, right? 0.5. So I'll write in 1/2 here just because I'm thinking unit circle in my mind. But if you want to put 0.5, that's fine too. All right, so I know this one, and this one, which means I have my tangent line now, right? So my tangent line is y equals, or sorry, I'll do y minus y1, or y0, which is square root 3 over 2, times m, which was 1/2, we just found out, and then x minus pi over 3. Or if you were looking in the back and they write it as L of x, they're going to write it something like this, square root 3 over 2 plus 1/2 times x minus pi over 3. Something like that instead. But we want to evaluate this at the x value we were actually given, which was the x value of 1. That was the original x value that we weren't too fond of. So we're trying to evaluate this at 1. And this is the part where that's all well and good, except that because I've got radicals and pi's in this problem, I have to use the calculator right now anyway, don't I? I do. So I'm going to have square root 3 over 2 plus 1/2 times 1 minus pi over 3. So be careful with your parentheses that things get multiplied in the right order and so forth. But what do we get for our approximate value of sine of 1? And let's go with 4 decimals. 4 is the next one? Okay, 8,424. All right, so my approximate value for sine of 1, or actually, you know what, your problem actually started out saying 1.0, so I'll write it just like it was originally. It's approximately 0.8424. Now, that is close to what we started with in 2 ways. Number 1, the approximate first value that we've got for the value we know was square root 3 over 2. And Christian, you told me what that was in the calculator. What did it say for what was square root 3 over 2? 0.866 something or other?
Yeah.
Right? And this is 0.84. So I mean, obviously that's fairly close. It's off in the hundredths place, but it's fairly close. The other thing you can do is you can actually hit in your calculator sine of 1. And what value is it that you get when you hit sine of 1? 0.8415, which means that we're actually accurate to 2 decimal places, not even just the one that we've had before, right? So this is a fairly accurate estimate is what this is. All right, we're going to generalize this now and to use it when we don't actually have an equation. So we can extend this idea to a set of data. So we're going to look at a table is what we're going to look at, where no formal equation for the function is given. So we don't have an equation, we just have a table of information. We simply use the closest x value to our desired x value and the closest 2 points to calculate the slope of the slope nearby to our x value. And that sounds convoluted, and it's actually quite easy. So let me show you real quick how to do that. So we have a sensor, and it measures the position of a particle t microseconds after a collision. Information is given in the table, and we're going to estimate the position of the particle at times t equal to 8 and t equal to 12. So if you take a look at this table, what you see is t equal to 8 means that the t values that we care about are 5 and 10 because they are the closest ones to the t value of 8. Are you with me so far? 8's between 5 and 10. So what it's going to say then is I'm supposed to be calculating y minus, you know what, I'm just going to write this way, y equals y0 plus m times x minus x0. So x0 and y0 come from the table wherever we are the closest to the x value we care about. I know it says t in this one. I should use the right variables. But we'll use t and t0 just because that way actually looks like the ones we're using. But I'm using the t value and the f of t value that are the closest to my t value of 8. So what will that be? Will that be the value of 5 or the value of 10? 10, because 10 is closer to 8 than 5 is, right? So this t0 value will be 10, and the y0 value will be the y value at t equal to 10, so it'll be 14. So far, so good? And then to get m, I use the 2 points, one on either side, and I calculate slope. So how do I calculate slope? This is like 6th, 7th grade, first time experience with slope. What do you do? Rise over run, exactly. So you look at the change in the y values over the change in the x values. In particular, on this one, we can talk about the fact that this is 14 minus 8 over 10 minus 5, right? What slope does that give me? 6/5. You got it. So this is 6 over 5. So my linear approximation, I'll call it L of x, is equal to 14 plus 6 over 5 times t, I shouldn't call it L of x then, I should call it L of t, times t minus 10. This is the linear approximation. And then I want to find this at the t value of 8. So we're going to do 14 plus 6/5 times 8 minus 10. And yes, we get a negative inside the parentheses. That's okay. That's not a problem at all. What do we get for L of 8? $11.6. That's right. And if the answer is 11.6, that should make sense because the t value is between 5 and 10. So our value that we just got is in fact between 8 and 14. So it's a reasonable expectation. All right. For the second one, we're looking at t equal to 12. So for t equal to 12, you'll notice that the 2 points that are nearest or surrounding t equal to 12 are at the t equal to 10 and t equal to 15. So we don't have the same slope either. All that changes. So we're creating a new equation with that information. So our new equation, we're going to use the t equal to 10, which is 10/15 for t. And for f of t, we have 14/18. And we're looking at t equal to 12. So for t equal to 12, clearly between these two, this is the t value that is closest to t equal to 12. So for y equals y0 plus m times x minus x0, for our equation here, we're doing L of t, because our variable is t. The y value at the value that we're looking at is actually 14. The t, or the x value, the value we're looking at is 10. And what we need to find is we need to find the slope. So we'll do the slope between these 2 points. So we'll calculate the slope, change in y over change in x. So we're looking at 18 minus 14 over 15 minus 10. So this ends up being 4 over 5. So this is the equation of our tangent line. Oh, one other correction here. Let me make that a t. So this is the equation of our tangent line, or the linear approximation. And we're trying to find out what happens at t equal to 12. So we're going to do 14 plus 4 over 5. Not a very good 4. Let me try that again. 4 over 5 times 12 minus 10. So we have 14 plus 4/5 times 2, which gives me 15.6. And again, notice just like on the last one, that 15.6 is in fact between 14 and 18, just like t equal to 12 is between 10 and 15. So we end up with this as our linear approximation at 12.